All right, so part 2 for 3-1 exponential functions and their graphs. Our essential question is going to be very similar to part 1, except for we're going to be looking specifically at exponential functions with base e, our famous number e. So we want to talk about and use that number e. So when we think through what this means, we're going to do a quick little calculation of what e is. And I know it always sounds weird to say the number e, but it's like a variable like pi that we use to represent a number that's very commonly found, and so it makes sense to have a letter for it so we don't have to write it out every time. So we're going to be able to recognize, evaluate, and graph those exponential functions. Then we're going to do a couple real life problems using both base e and regular numeric bases as well. So we'll do a little bit of both. So let's start with what natural functions are. So natural is the word that they give to things that have base e. So like if you remember natural logs, those inverses, natural functions have base e. So we're talking about things with base e. So it'd be something that looks like this: f of x equals e to the x. Remember, I think this looks like there are no numbers here at all, but remember e is a number. So we're going to calculate what e is. So the e is the base constant, and the x is the variable that you're raising it to. So notice again what the location of the variable is. It's up in the exponent. That's why we call it an exponential function. So here's what I'm going to have you do. We're going to have to do a quick little calculation here. I'd like you to do a sum for me. So e is approximately 1 plus 1 over 1 with this symbol. See if you remember what that symbol means. And we're going to go out a few terms here. So you can keep going. The more terms you do, the more accurate your expression for e is going to be. Plus dot, dot, dot. Remember what that means. Remember what the little exclamation point means? It means factorial. So like 3 factorial means 3 times 2 times 1. We're going to do that quick calculation. I want you to type this into your calculator. We'll go only out to that, that term with the 6 factorial. See what you come up with. All right, so when I did the factorials for each of those, 3 factorial 6, 3 times 2 times 1, 4 factorial 24, 4 times 3 times 2 times 1, etc. Add those all up. Hopefully you came up with the same thing. 2.7180, blah, 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 keeps going, non-terminating, non-repeating, just like pi. The approximation we affectionately use for e is the 2.718. So when you think e, I want you to always be thinking the number 2.718. So e, 2.718. So a little bit less than 3, so it's a little bit less than that. So when you're thinking as an estimate, that's what that's going to look like. So that base, 2.718, is bigger than 1. So think about what the graph for e to the x is going to look like. And I'm going to go ahead and just plot a few points here. Because the base is bigger than 1, that e value, it's going to be increasing for all values of x. Our domain is going to be all real numbers, again, just like any other exponential. The range should be the same as what it is for any other exponential, so bigger than 0. And the x or the y-intercept should be the same, should be at the 0.01. So all of those things should be the same. So if I do e to the 0 power, it's still going to be 1. E to the first, 2.718. E to the negative first, just go ahead and type it into your calculator there. Negative first, I got about 0.3679 something. We can't be that super precise in our little graph anyway here. So 0, 1, 1, 2.718, so a little bit less than 3, about a third. We know we have a asymptote, horizontal asymptote of the x-axis, increasing for all x, or for all values. So here's the thing. We can transform this the same as we do with any other function. So we can go up, down, left, right. We can flip over the x. We can flip over the y. All of the transformations that we've talked about for any other base is the same for these natural exponential functions that have a base e. You can also do any sort of calculation you want in your calculator with e, but let's just take a peek and make sure that we're okay with that as well. So e, you can find it in a couple different places. So see if you can locate it on your keypad. One of them is second ln. That's kind of a nice one, especially like in this case when we want to just do a quick calculation. It already gives you the exponent. So like 1. Let's go out to the 10,000ths again. So 822, the 1 would stay a 1 because of the 1 after it. So we can get a pretty good approximation. Can you find another e on there though? So take a look at your keypad. Right above the divide symbol, you also have an e. Notice it doesn't give you the exponent. So if you just do e, if you ever forget what the number e is, great way to figure it out. If you use this one though, the second divide, and you do want to raise it to a power, you do have to put in the power yourself. So usually if I'm doing a power, I'll do the other one. So it's just a little bit quicker. You can use the one-to-one property. The one-to-one property is the same in this situation, because if you have e to the x equals e to the y, the bases are the same. That means if and only if, we'll use our abbreviation for if and only if, then x must be equal to y. It's the same thing because the bases are equal. It's kind of a cool deal. So let's take a look at this one. Notice the bases are both e. So it's saying, hey, e to the x squared plus 12, when is that equal to e to the 7x? That means if the bases are the same and the two functions are equal, we must be looking for when x squared plus 12 would be equal to 7x. Remember our graphing approach, right? We could graph both of these and see where they cross. We could graph this side as y1 and this side as y2 and see if we could figure out where those two graphs cross. But we can also do it algebraically, which for some people may be quicker. What degree equation is this? Highest degree variable you see, degree 2. How do we solve degree 2? By factoring. If it doesn't factor, what's your backup plan? Quadratic formula. So hopefully with one of these options we'll be able to solve. To be able to do either of these methods though, we need to make sure we're equal to 0. So get all of your terms. Oops. I'm going to put the 7x next here, descending order. On the same side, get it equal to 0, and then we're just going to hope that this factors. Can you think of any numbers that multiply to a positive 12 that would add to a negative 7? So how about 3 and 4? The signs have to be the same since it's negative. They're both minus. So we get x equals 3 and x equals 4. Okay, so what this means is there's actually two different places where there are solutions for this graph. There's two different locations where the x's are the same. So we can definitely have more than one value for these exponential functions. So if I plugged in either 3 or 4, I would get the same answer on both sides. So if you take a look at that, it should be equal to 7 times 3. So 3 squared is 9 plus 12, which would be 21, which is the same as that one. Plug in 4, you're going to get the same idea. So the one-to-one property, great tool as well. All right, let's take a look at some applications. Let's really kind of dig in. E is just a number that we use as a base, and it comes up in a lot of different areas. Hopefully you remember from Algebra 2 about calculating account balance and interest. It's a great example of using exponential functions and how important it is to invest your money early because it grows so quickly. So we're going to look at the compound interest formula that you would have remembered from last year, and I'm curious if you remember this one. So pause the video. Do you remember any formulas that have to do with account balance for interest? So maybe it's coming back to A equals P, 1 plus R over N to the NT. My goodness, look at all the letters. So it says after T years, so T is time in years, the balance in your account. So A is the account balance, like how much is in your account. Principal P, what's the principal? That's the starting amount. That's the amount that you start with in your account. So like if you open your savings account with $100, it would be the $100. The annual interest rate, R, so R for rate in decimal form. That means if you have 4% interest, that would be 0.04. Is given by this formula then. So A is your account balance, P is your principal, R is rate, T is time. Gosh, there's one thing left to talk about, N, the number of compoundings per year. Okay, what do I mean by that? So if you compound your interest, say monthly, how many times per year then are you going to get interest on your account? Monthly would be an N value of 12. So monthly means it would be 12 times per month. Once per month, you're going to get interest. Now, if you think about it, the more often your interest is compounded, that's better for you. Some might say it's in your best interest. Pun intended. But think about that, because what happens with your interest? Well, they add it onto your account, right? So say you earn $3 in interest, now your balance is $103, and then you're going to earn even more interest on that because the principal's larger. So it's in your best interest to compound more frequently. What if they say quarterly? What do you suppose quarterly would mean? What would your N value be? How many times per year would quarterly be? Well, how many quarters are there in a dollar? 4. So that would be 4 times a year. Sometimes they say semi-annually. This one kind of messes people up sometimes. Semi-annually. Well, semi means what? Like semicircle, half a circle. So semi-annually, twice per year. So semi-annually would be 2. So those are some of the most common that you'll see. Most banks usually quarterly, but often they'll report your earnings monthly then. So you get a statement every month, but they don't give you interest every month. Some do though. For continuous compound, so this is what if they could continuously give you interest infinitely many times, which would be awesome, physically impossible, but awesome. We get this account balance. Some of you might remember this affectionately as the PERT formula, P, E to the RT. Remember, E is our base, 2.718. R is still interest rate as a decimal. T is still time in years. Notice there's no N. Well, because if you're doing it infinitely many times, how would you plug an N in there? That doesn't make sense. So when we're talking about PERT, we're making the comparison. If we could do best case scenario and do this infinitely many times, well, how much interest would we earn? What would our account balance be? All right, so let's take a peek and we're going to do that comparison. So I have those two formulas up there. We're going to do 4 different things to compare. What do you think would give us the best interest rate or the best amount of interest and therefore the best account balance at the end of a period of time? So we're going to make some comparisons. So for part A, we're going to do compounding monthly. Okay, so remember what monthly means. That means once a month, so that's 12 times per year. For part B, we're going to do compounding continuously. All right, so continuously, that means infinitely many times. And then we're going to compare quarterly and semi-annually. So we're going to look at all of those options. So for part C, we're going to do quarterly. So remember what quarterly means, 4 quarters in a dollar, 4 times per year. And then semi-annually. So semi-annually means twice per year. So just keeping track of our N equals for each of those. Okay, which of these is going to give you the biggest account balance at the end of the same amount of time? So keeping time the same, interest rate the same. Which one compounds most frequently? It should be letter B. Which one's going to be the least? So which of these would give you the lowest account balance at the end of that period of time? It would be the least number of times compounded, so that should be D. So this should be the biggest answer, and this should be the least based on what we know about compounding. All right, so let's go ahead and do those calculations. So you're trying to find the amount in the account. So in those formulas, what are you searching for? You're searching for A, the account balance. So for each of these, we're trying to find A. After 10 years, okay, so what does the 10 represent? Well, that's your time. And time is always measured in years because these are longer term things. So what if it said like 10 years, 6 months? You would have to convert the 6 months over into years. So instead of saying 6 months, you would say what part of a year is that? So 6 out of 12, it's half. So you would say 10 and a half or 10.5 years. Always make sure it's just in years. If $6,000 is invested, okay, that means that's what you're putting in originally. That's your P value. So the P is the 6,000 at an interest rate of 7%. So that means your R, your rate is 7%, but as a decimal. So 7 divided by 100, so 0.07. I guess you could leave it 7 over 100, but I think it's easier to type into your calculator as a decimal. All right, so monthly then, we're going to be using this top formula, monthly, because it's somethingly, right? We have an N value, so we can put that in. So our principal, $6,000, and then 1 plus interest rate, which is 0.07, divided by monthly is 12, and then raised to the 12, so 12 times per year, times how many years? 10. Okay, now I want to talk about what some of these numbers actually mean. And this is really important to me that you understand what's happening here. So let's take a look at this base first of all. Can you do the 0.07 divided by 12? So the 0.0 divided by 12. So I'm going to go ahead and jump over to my calculator here. 0.07 divided by 12. That 0.00583333. All right, so which is basically, if you think of this as a percent, move it over 2 places, like 0.58% per month. So here's what 7% means when the bank talks to you about this. If you've ever heard of APR, annual percentage rate, like they talk about that sometimes on commercials for financing for cars, things like that. That's the annual percentage rate. That means the 7% that they're talking about is the interest you get for the whole year. But they don't give you 7% every time. They give you the 7% divided up amongst all the times they're going to give you interest. So if it's monthly, they're going to take 7% and divide it by 12, and that's actually what percent you get per month, which is less than a percent. It's a little bit over half a percent, 0.58%. So you don't get much per each time. So when you think about what this means, I'm going to just write this. I would always just leave it on my calculator. Your base, oops, 0, 0, get my other 0 in there, is really, it's bigger than 1, right? 1 plus this. If your base was 1, that means your bank isn't giving you any interest. Don't go to that bank, because remember, 1 to any power is just 1. But the plus part, that's the part that the bank is giving you each time. So the 0.00583 repeating is that little bit over 0.5% per month that you're going to get. All right, now here's the other number I want to talk about. The exponent, 120. So for 10 years, 12 times a year, what's the 120? Well, it's how many times you're going to get interest. So they're going to do this interest calculation for you 120 times. So 10 times or 10 years times 12 times a year. So it's the how many times you get interest. And then literally this is going to be a plug and chug on your calculator. Now let's talk about how I would type it in. Some people just type it exactly as the red is written. They just type it in. Some people do the calculation that I did first, like order of operations, add 1 to it. So you're starting on the inside, working your way out, raise it to the 120th power, exponents right before multiply, and then take your answer and times it by the 6,000. So it looks like for this first amount, if I'm going to do this monthly, it looks like I'm going to come out at $12,057.90. What would you round to? Think about that for a second. If it's money, what would make sense? What's reasonable? Probably round to the nearest penny, right? You would want to have to the nearest penny. So that would be 97 cents. So we would have $12,057.97. Okay, so here's how we're going to compare this now. I'm going to go ahead and do the other somethinglies. I'm going to have you try to type those in. So I want you to write out what do you think this equation would look like quarterly, and then semi-annually. Type those in, see what you get. All right, so for quarterly, that means it's going to be 4 times per year for 10 years. So that means instead of having 120 out there, now I'm only going to have 40 times. So 4 times a year for 10 years, there's way fewer times you're going to actually earn interest. The other part of this is how much interest do you get each time? Well, it's 7% divided up over 4 units of time. So you get 0.0175, which means you're looking at 1.75% each time. So 1.75%, and you get it 4 times. That gives you your total of that 7%. So again, we can just calculate that in there. So I'm going to go ahead and add my 1 to it, raise it to the 40th power, and then we're going to multiply by the 6,000 so we can see what that would be. So 12,009, and then rounded to the nearest penny would be 58 cents. And 58. Okay, so see how that compares. It's less, right? It's less than the original that we came up with was the 12,057. It's less because we're compounding a fewer number of times. So you're not going to earn as much interest. All right, so semi-annually. So again, the comparison. So we're only doing this twice a year. So it's 0.07 divided by 2, and then 2 times 10. So what that means is you're only going to have 20 times over this period, 10 years, twice a year for 10 years, where you earn interest. And what part of interest do you get each time they do it? Well, 0.07 divided by 2 would be 0.035. So you're getting 3.5% each of those times. So 2 3.5s make a 7, right? So go ahead and type this one in, see what you come up with. So for this one, I came up with 11,938.70 to the nearest penny 3. So 11,938.73. So 11,000. Make sure you label things too when you're writing your answers. Again, we said this should be the least, and it's for sure the least of these because we're only doing this 20 times. So it does not get you as much interest, so your account balance won't be as much. You're not adding in as much. Now, remember the concept here. What else could make your money grow faster? What are some other things that potentially could change? Well, how about how long you leave your money in? So the time. The longer you leave your money in, the more you're going to earn. How about starting off with more money? What if you put in 10,000 instead of 6,000? Well, yeah, then it's going to be more. How about the interest rate? What if your interest rate was more? That would be awesome. Now, most of you, if you have a savings account, you're not earning 7% interest for sure. It's probably way less than that. Check into that if you're not sure what your interest rate is. It's probably tiny, but it's better than in a piggy bank under your bed or something. So it's a little bit easier to earn money when you're earning interest than it is just to sit there. But it's not going to be a lot in some of those low risk funds. That's why people invest in stocks and things like that to earn more interest. They're riskier though, but you can earn more. So think about the things that can change and how that would have an impact on your money. All right, now let's compare back to this continuously. What that means is you're using PERT, A equals PE to the RT. There's no N you can put in. The keyword there, continuously, if it could be an infinite number of times. The principal though is still 6,000, And then our interest rate is still 7%, and that's over 10 years, and we can type that in. So when you're using your graphing calculator here, I would probably just type the whole thing because it's not as difficult as maybe some of the other ones. I would use the e to the and then 0.07 times 10. Some people maybe would multiply that right out. And this would be $12,082.52. So 12.82 and 52 cents. So notice your account balance is the most, not by a ton, but it is the most if we could do this an infinite number of times. So it's a great example of using exponential growth to describe real life situations. Now, what we assumed here though too is we didn't do any deposits or withdrawals, right? So we didn't add any extra money in along the way. We didn't withdraw or take any out. We just assumed the money was sitting there. Obviously, if you put more money in as you go, you will also end up with more money at the end. All right, we're going to look at two other great examples of things that use exponential growth or decay. Let's talk about half-life for a second. Maybe you've heard something like that. We're going to take a look at nuclear energy for a second. So I'm going to give you a background on something, and maybe this is familiar to you. Basically what you look at when you talk about nuclear, we're going to talk about incidents, I guess, issues that happen, they can rank them based on how severe they were. So I want you to think about Chernobyl, if you've ever heard of that. Chernobyl is a city where there was in Soviet Union, former Soviet Union, that had just a terrible, terrible, terrible nuclear incident, reactor meltdown problem. Japan also had one too. Those are the two historically the worst that have ever had that have been given the highest ranking, the 7. So Chernobyl, if you want to Google it, it's a very interesting story there. So when you think about that and actually try to figure out when that was too. So it's in the most recent issues that we've had that only 2 have ever gotten a 7. So here's the situation. In 1986, this nuclear reactor incident in Chernobyl spread toxic radioactive chemicals, basically plutonium, all over hundreds of square miles, which is no longer able to be habited. Right? They can't use that land. It's completely toxic, and they evacuated the city. It's a ghost town. It's super crazy. If you look at pictures of it now, there are trees and things growing back, and there's those things, but it's not safe to be habited because of the level of toxins in the air and in the water and in the soil. So, and this is why we're going to talk about why using an exponential equation. So I want you to take a look at the equation that models what's happening here. So they're talking about t as a time, so looking at a time in years. And P is the amount of plutonium still left, this plutonium 239 still left in that area. So the exponential decay, why is it decay? Look at your base. What is the base? It's the half. That's why they call it a half-life. There's only half of it left after a certain period of time. So it's decaying half each time period. Now the problem for Chernobyl and other places is the half-lives of these things are ridiculously long. If you take a look at this 24,100, that is the half-life for this plutonium. So that means it takes 24,100 years for half of the material to decay. So think about how long that's going to be. Now the 10, let's talk about the 10 in this equation, what the 10 would represent. The 10 is what they're using as the initial amount of plutonium. So 10 pounds of plutonium. So this is kind of like your A value, your starting value, your initial amount. So sort of like in our last equation when we talked about the principal, like the initial beginning amount, that's what that 10 is. It's the starting amount. So if you start with 10 pounds. So say you had 10 pounds of plutonium and your half-life was 24,100 years. And your P is your amount of plutonium remaining after a period of time. So the amount of plutonium that's left after a period of time, and the time is in years. Now, it's going to take a while for this to happen, so just think about, we're going to make a little table here. So I'm just going to say if we have time and the amount of plutonium, if you do one half-life, so that means 24,100 years. So 24,100 years, that would be one half-life. How much would you have left? Well, if you start with 10 pounds, you're only going to have 5 pounds then remaining. So after one half-life, you'd have 5 pounds. Okay, what would 2 half-lives be then? So just think about, I just want you to get an idea of what's happening here. 2 half-lives would be another 24,100, which would be 48,200. It'd be half of the 5 pounds that you had here. So half of 5 pounds would be 2.5 pounds. Okay, so think about this. After almost 50,000 years, you still have 2.5 pounds there. How about 3 half-lives? So 3 half-lives. Well, that would be another 24,100. So 72,300. There would be half of 2.5. So 1.25 pounds left. What about 4 half-lives? Should be saying lives, I guess. Another 24,000 onto there. So 96,400. There'd only be half of this left, 0.625 pounds, etc., etc., etc. Now think about that. It took almost 100,000 years to get under a pound. Okay, so this is a very slowly decaying kind of thing. Is it ever going to reach zero? Think about exponential decay equations. So think about when you graph exponential decay, don't we have a horizontal asymptote? Right? And we didn't have any vertical shift on this. There was no plus or minus at the end over here. So we have a horizontal asymptote at y equals 0. So that means it never quite gets there. So this radioactive stuff, it gets smaller and smaller and smaller, like really trace amounts, but you're kind of approaching 0 there. Could it ever be entirely gone? Maybe. But it's going to take a really long time, right? So that's what we're going to be thinking about here. So here's the question, now that we have kind of what the model is doing. I'm going to use 0 to represent 1986. So that's when this incident occurred. So my t equals 0 is going to represent 1986. My question for you, how much of the 10 pounds is going to remain in 2086? Okay, so we're starting with this 10 pounds. We know it's decaying. We did a little bit. We talked about this. We know how long, we did a little table. It took 24,000 years to get down to 5 pounds. I'm asking you for when. When would 2086 be from 1986? Well, how many years after 1986 is 2086? Well, that would be a t value of 100. How much would be left after 100 years? Think about that. That's like an entire many generations here of being able to be able to inhabit that. How would you calculate the amount present after 100 years, or in 2086? Well, that's just meaning the t is 100. So I'm just going to substitute in 100, see what I get. So 100 divided by 24,100. Can you do that calculation on your calculator? Let's see what we come up with. All right, so I typed it in, 9.971 blah, 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 blah. Okay, so the amount of plutonium left after 100 years was 9.971 about pounds. In other words, you've barely lost 0.03 of a pound after 100 years. Basically, it's all still there. So you can see what a huge and devastating impact this had on the community, because it's still going to be there. They're not going to be able to have a habitation in this location for many, 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 many years because of the slow decay of plutonium. So let's say 125,000 years. How much would be left then? So instead of me asking you how much after only 100, let's think super optimistically, 125,000. Not that any of us would be around to see that, but what about 125,000? So go ahead and type that one in. See how different your answer is and how you're feeling about 125,000 years later. All right, so after 125,000 years, which is approximately 5 half-lives, right? 24,000 is pretty close to 25. 25 times 5 would be the 125. So we get down to just under 0.3 of a pound. So we get to about 0.275 pounds. So down to approximately a quarter of a pound, get pretty close. So 125,000 years, oh, that's crazy. That's so long. So when we think about where we're headed with this, that's why these nuclear situations are so dangerous, because the half-life just takes forever, 24,100. So make sure you understand in the model, though, what each of these values represent when we're looking at it. So like this starting amount, the initial amount of the 10, what's happening, so it's decay, it's a half. The final amount, right? So this is always the final amount of whatever it is. is starting amount, and then the T is your time, and then the time per half-life. So you're figuring out how many cycles of that. So think about what makes sense. If we go back to our table, we said after about 100,000 years would be about 0.6. So after 125,000 years, kind of a reasonable answer, then that it would be less than that. So one really great example of exponential, in this case, decay. All right, we're going to talk about Newton, Sir Isaac Newton, famous English mathematician back in the late 1600s and 1700s for our last example here. This is called Newton's law of cooling, which basically is the science that governs how things cool off. So imagine you take out, say, your pizza rolls that you have made in the oven, because let's all be honest, pizza rolls are way better in the oven than they are in the microwave. We all know this. We microwave them anyway because we want them faster, but they're better in the oven. So you take them out of the oven and you want to pop one of those guys in your mouth right away. You know you shouldn't, but you really want it. You eat it, you pop it in there, and it just burns and all that good stuff. So you got to wait. You got to have it cool off. So your pizza rolls are going to cool off. Say there was 350 in the oven that you baked them at. After a few minutes, it's going to get cooler. They won't be so hot. You won't burn yourself. We all know how this works. Or if you take something out, say it's really hot outside and you bring it into air conditioning, it's going to cool down, just like you, right? We know this. If it's summer where we get super hot, we come inside in the air conditioning, oh, we cool down. Let's talk about how something's going to cool down and think about what all these values are going to represent. So T, this capital T, is temperature after a period of time. So temperature over time. So it's going to be the temperature of whatever your object is, the pizza roll, you, whatever it might be. Remember what the number is out front of the exponential part. That's always the kind of something to do with that starting or initial, what's happening there. In this case, the A value is kind of tricky. It's the amount that your object needs to cool. The amount the object can cool. Now, another way to think of that, it's the difference between the starting temperature and the ending temperature. So some people think of the A as the difference between what your item starts at. So like say your 350-degree pizza roll, and then the ending temperature that it can ever get to, which would be like room temperature, right? Wherever you put it. So the difference between the starting temp and the surrounding temperature. Like what do you put it into? So for me, that would be like from the oven to my room temperature. E, we know what E is. It's a number, 2.718. K is the constant of cooling. So K, kind of like Campgrounds of America, it's the constant of cooling. Every single object out there has a constant of cooling. It's really easy to measure. You measure the temperature initially. You let some time elapse that you also measure, and then you measure the temperature again, and you can calculate your constant of cooling. M, notice where it is. Now think about what determines when you can eat your pizza roll. It's how hot you can handle it, right? No, it's how long you let it cool, right? The longer you let it cool, the lower the temperature is going to get. It's not going to keep getting lower and lower and lower forever, though. It's going to slow down and gradually approach room temperature. So M is the time to cool in what? It's an M. In minutes, right? Things cool off in minutes. You don't wait decades to eat your pizza roll. That'd be gross. It'll be nasty. You don't wait hours either. Do you? Be totally cold. You wait minutes. Things cool off very quickly. So the time to cool in minutes. All right, I want you to think about graphs now for a second. What does adding or subtracting something at the end do to your graph? It's a vertical shift. So the C is your vertical shift. What do you suppose the vertical shift is going to be? Think about what exponential decay graphs do. And I know it's decay because that's a minus, right? So it's going down. Well, think about it. The temperature's decreasing, right? Your pizza roll temperature is going to start off hot and it's going to gradually approach an asymptote, right? What would that asymptote be? That's your vertical shift. That's your C value. Well, that's the room temperature, the surrounding temperature. So this is the surrounding temperature that you're putting your object into. So for me, if I take the pizza rolls out of the oven and set them in my kitchen and it's 70 degrees, the C would be the 70 degrees, that surrounding temperature. So it's going to cool down and approach that value. Now, in reality, it will actually equal that value. I know we talked about it never touches the asymptote. In this case, it's going to approach the asymptote and it's going to probably equal it as well because we can get to that temperature if we let it cool off that much before we eat it, right? All right, so true story. True story. So this is a great application of Newton's law of cooling. If anybody ever tells you that math isn't useful in real life, they haven't probably done this in their life, and they probably will at some point. So if a can of pop is at room temperature, 70 degrees, so say it's in the store, like Cub, whatever, and it's put in the trunk of a car at 15 degrees Fahrenheit, so it's winter, it is cold. What would be the temperature after 30 minutes if the constant of cooling for pop is 0.05? Would your can be frozen? Okay, so why am I bringing this up? Telling a story about a friend. I'm using air quotes here. A friend. This couldn't have possibly happened to me. So if you buy pop at Cub and you put it in the trunk of your car and you say, forget about it for a long time, what do you suppose is going to happen? Maybe you've done this. What happens to the can of pop? They explode. It was like the 4th of July in my trunk. Not kidding. I had cases of pop. By the way, Diet Coke is the worst. It froze first. What happens? The can, when it freezes, it expands. The can bursts, and you have this just absolute fireworks going on in my trunk. It was absolutely crazy. So that was a pull over to the side of the road and be, oh dear, this is going to be a mess. So math is real, folks. It happens. So my question to you, would your can of pop be frozen after only 30 minutes in this trunk? So let's see what happens. Mr. Zabel was not happy with me in this scenario. All right, so Newton's law of cooling was in effect. So I'm looking for the temperature after a period of time to see if it's going to be frozen. Frozen in Fahrenheit, remember, is 32 degrees Fahrenheit, is freezing. So was it that or less? Already after 30 minutes. All right, so the A value, the amount that temperature can cool. This is a really important calculation. What temperature is my pop starting at? 70 degrees. How cold can it get? It can only go down to 15 degrees, the surrounding temperature I put it in. So the A value is the amount that it's going to cool total, which would be 55. So just be really careful. That's the part that people usually miss, is that amount that it's going to cool, that slope. We've got E to the negative. They gave me the constant of cooling. Again, everything has its own. Time in minutes, 30 minutes. So after 30 minutes, so that's your time. If it said half an hour, make sure you convert it to minutes. You wouldn't have put in a half there. You would have put in 30 still. And the other thing people forget, the plus C. What is the coldest that this pop can ever get? The surrounding temperature. So your C value is the 15. So don't forget the plus 15. Your asymptote in this situation, when you graph this, is moving up to 15 degrees because that's the coldest that that's ever going to get. So just be careful. Let's type this in. If you graph this equation and just used an X here instead of the 30, what would you get would be all the temperatures over time. You'd be able to predict at any period of time what the temperature would have been, which would be kind of cool too. But for this purpose, I just want to see if it's going to be frozen or not. We'll get into more of those specific solvings. All right, so be super careful as you type it in. Make sure you get all those values. 27.27, so about 27 degrees. So the temperature after only 30 minutes, 27 degrees Fahrenheit, about. Now, not frozen solid by this point. I left it in there way longer than 30 minutes. It was probably many hours because I was just driving around doing stuff and then kablam in my trunk. But it was already 27 degrees after 30 minutes. So maybe not frozen solid, but below freezing and on its way. So Newton's law of cooling is a great example, again, of something that uses natural exponentials, so e to the, but is a great example of how we model exponential growth and decay.